Thank you all for coming today. Today's going to be a brief introduction to R. And as for introductions, my name's Alex Townsend. I'm an application specialist at the Research Computing Center. Our workshop helper today is Marcelina Nogales, who is also an application specialist at the Research Computing Center. The Research Computing Center is just as a quick introduction to the Research Computing Center, we are the main supercomputer on campus. So whenever you run data analysis or run computations that start to eat up your laptop, start to take way too long, we're the place you would generally go to do really big computations or computations that are going to take a really long time. Now, for the purposes of this workshop, you don't need to worry about an RCC account or anything. For those of you who are using R through the Research Computing Center, we've got pre-made workshop accounts set up for you. I'll go over a little bit more about the Research Computing Center later on at the end of the presentation. And also, as part of logistics, for anyone who's online, if you have questions, please put them in the chat, and either Marcelina will answer them or she'll direct them to me. So to get started, R is a programming language as well as a statistical package. We have, like, the Research Computing Center has it available through a number of our different applications. It's available through the HPC terminal or through the Open On Demand web interface that we had slides on earlier on when everybody was just starting to trickle in. So this is a brief just showing of the Open On Demand interface. Traditionally, supercomputers are command line only. So if you've ever gotten on Windows or Mac and you pulled up the terminal, or God forbid gotten the command prompt show up and you wonder what in the world is that? That command prompt is sort of the old school interface for computers, and it's how most interactions between home computers and supercomputers are done. Now, that's not very user friendly, and most people don't start out with the command line. So there's been a large push lately to get people to get better interfaces, and Open On Demand is one of these. So the Open On Demand interface just allows you to sort of point and click and get access to specific things that you need, and access to RCC's big, powerful computers. So we've got a bunch of interactive apps, of which RStudio is one. And all of the examples I showed today are going to be through this interface. But just to reiterate, if you're working on your own computer, if you have RStudio, you're good to go. So this is just an example of setting up a job through Open On Demand. Every interaction you have with a supercomputer is called a job. So basically what that means is you ask the Research Computing Center's job controller for an allocation of resources and time, usually a bunch of CPUs and a good amount of time. And then the Research Computing Center our systems will go and find those resources for you. So what you'll do when you start a job for RStudio on our systems is you'll fill out this form, you'll hit the launch button, and then you'll sit and wait until you see that green box show up on your screen. And then when you hit connect to RStudio server, you will just get taken to the standard RStudio interface. So that's it for the basic introduction to R with the actual supercomputer. Now let's get to the important stuff, which is actually R. So R is essentially a scripted or an interpreted programming language. As I said before, it's both a programming language and a statistical analysis package. So if you've ever looked at like Stata or SAS or SPSS, those things are very similar to R in the sense that you can do all the same things with those packages and languages that you can do with R. The main advantage of R is that it's sort of twofold. It is a full-fledged programming language, so you can actually write your own functions. You can write your own statistical analyses in R. You can even write pretty much anything you would want to any kind of program you would want to write for a computer, you can write in R. The other big advantage, and probably the main thing for applications and for actual use within the research field, is that it's free and open source. Anybody who's done research, or anybody who's been a grad student like me, knows how hard research funding can be to come by. So it is very nice to have. It's very nice to have a free, open source programming language available. The other neat thing about R is that it has a huge database of both statistical functionality as well as pre-installed data sets. So you can actually get a whole slew of data sets just built in for you to start working with. So, like I said, R is essentially an interpreted language, and so what I mean by interpreted language is that when the computer reads R code, it's going to go line by line. It's going to start reading just like you would read code or just words on a piece of paper. It'll read the first line, and then it will do whatever the first line says. It will read the second line and then do whatever the second line says, and so on and so forth. This is actually very different from the way a lot of other programming languages like C++ or Java or other things you might have seen before work. A lot of other programming languages like C++ and Java are called compiled. And what that means is that the computer will read the entire code first, and then it will build something called an executable file, which is essentially, it'll take the entire code and translate it down to zeros and ones, machine code, essentially, so that which is the only language the computer can actually understand. Interpreted languages have a layer between the zeros and ones and the actual code that you read, which is another program that's actually reading the lines of code and executing them in the background for you. Interpreted languages generally are a lot easier to get started with. They generally have a lower learning curve, and they're generally a lot faster to get up and running with. But compiled languages are generally faster. So if your application has really needs a lot of power, and you really need control over exactly what pieces of memory in the computer you're accessing, then you might want to use a compiled language. But if you just want to get your work done, an interpreted language is usually what you're looking for. And R is one of those. So once you load the RStudio interface, either through Open On Demand or through your own computer, you'll see this big screen with a bunch of windows on it. On the top, in the top right-hand corner, you'll have a window that says something like Global Environment. That is a window that will basically hold a list of all of your variables and data sets that you have loaded into the current workspace that you've got. So the whole window here is often called a workspace, and this is basically the environment in which you're doing everything. You're issuing commands to R, or you're loading data sets, or you're creating variables which in computer terminology, variables are just labels for something. So if you've taken algebra or you've gotten it into math, and a variable is exactly the same thing as it is in math. On the bottom right-hand corner is the File Explorer window, which is just like opening the file. It's just like opening the file browser in Windows, or I forget what the term is in Mac, but it's the file browser in Mac. And that'll just show you the list of all the files that you have in the current working directory. And the current working directory is usually what would be considered home or My Documents in Windows. And so by looking at that, you can actually point and click on the files in there, and you can either load them into R automatically. You can open them and look at them, and this will give you an idea of what's in your current workspace that you can use. On the bottom left-hand side is the command window, and this is where we're going to be doing most of our work with R. This is where you type individual commands. This is where you'll actually run code. In the top left-hand corner, you'll have the results and text editor window. So whenever you create a new file or open a file, it will be opened in that results and text editor window. And by text editor, I mean it's sort of like a really stripped down version of Word. So you open a text file or a CSV file and you can edit it, and you can edit it in the top left-hand corner. Also, whenever you run a piece of code, particularly whenever you run like a big script that's not just one command, you'll actually get the results up in the top left-hand corner. So also there's also the typical file browser, so you can click File and save files as. You can rename files. There's also the little green plus button in the top left-hand corner, which will allow you to open a new file. And I said that R is both a programming language and a statistical analysis package. So just like if you've done Excel or SAS or anything like that, you can actually create a new file and type a whole sequence of commands into a file, and then you can save that file and run it, and it will do exactly what I said an interpreted language will do. It'll read the code line by line and do everything you say there. That's really nice, because then you don't have to be sitting there typing the command one at a time. So the first command, the first program that most anybody learns in R is sort of the Hello World program. If you type in the R command window, print open parentheses and in single quotation marks hello R exclamation point, and then close parentheses, and then you hit enter, you will see that the words hello R will be printed to the screen right below. It will be right below where you typed that command in the command window. This is both the simplest program you can write in R, and also an introduction to one of the more important things. It's one of the more important sort of things you can learn with R. The print statement is very versatile. It's not just about printing words or letters or these things which are called strings, which are whole sentences. You can also use the print command to print out the values of variables, or you can even have it print out whole data sets that are in your current environment. And as a result, the print statement is very useful for kind of keeping track of the flow of your data, and it's useful for keeping track of the flow of your programs, the flow of what you're doing. And also, if anything goes wrong, it's good to have print statements everywhere in your code, because then you can catch it right when something starts to go wrong. Another thing you can do with R is you can read and write to individual files with code. So one of the most important file formats that you'll see with data analysis, whether it be bioinformatics or statistics or anything like that, is the CSV file format. CSV is kind of like Excel, except it's way simpler. Excel has a bunch of weird stuff in the actual file format that can make it a little hard to read. A CSV file is just a simple text file where every field is separated by a comma. And R has a nice little function called read.csv, which will allow you to read a CSV file in your current working directory, and it will turn it into a table, which is called a data frame in R. And once you run the read.csv command on a CSV file that you have in your working directory, you'll be able to take that. It will be assigned to a variable called myData, which you can then either print out or you can actually use in farther steps in your code. So there's also a write.csv file in R, which you can use to take a data frame or a table that you have that you've created through previous steps in your analysis. You can take that table and write it out and save it to a CSV file for later use. this kind of thing is really important because if you're doing data analysis, it's kind of not very helpful if you can't save your results for later use. So another command that's really useful is if you're working with R through the command line, so just through the terminal window, which R does allow. R has both the RStudio version, and if you've installed R, you can actually use it through the terminal too. There's a command called rcmd batch, which basically allows you to run a whole series of commands saved in a file in something called basically non-interactive mode. So if you have a whole bunch of commands in R that you want to run and you just want to sort of set it and forget it and wait for it to finish, then you can write your list of commands in a file, save it, and type rcmd batch in the terminal and the name of your program .r, and then it will just start running the code in the background. And once it's done, you'll have a output file which will be whatever the name of your code is .rout, so ROUT, and in there will be the results of all the commands you ran. And this is really useful. This sort of thing is really useful if you're doing really big computations or you're doing analyses that are going to take a really long time. And if you get into really big data analysis where you have hundreds of thousands or even millions of observations, then you might, if you're just sitting there looking at RStudio, you might be sitting there for a couple hours waiting for the results to be given back to you. So by doing this, you can just sort of run the commands in the background and go do something else for a while. I'm sorry?
What is HPC system?
Oh, sorry. HPC system is just another term for RCC. HPC stands for high performance computing, and it's sort of the system that the Research Computing Center runs. And for those of you online, the question was, what does HPC stand for? And it stands for high performance computing. So R comes with a whole bunch of built-in data sets and a bunch of built-in libraries. In fact, later on in this presentation, we're going to use three built-in libraries: the parallel library, the cluster library, and the datasets library. Many of these, and a lot of these packages in R come with their own built-in datasets. So the package datasets, for example, is pretty descriptive of what it contains. It contains a whole list of datasets for just about everything you can imagine, from like car miles per gallon to simple biological datasets. You can also install R packages on your own home directories or on your own computers if you want. And there is a long list of different packages available. There's packages available for even like specific subfields like psychology. And if you're in bioinformatics, there's actually a whole set of packages called Bioconductor, which is sort of its own sub-package manager that within that environment contains hundreds of its own libraries. So there's a very, very, very rich ecosystem of libraries that you have available to work with. Okay, so if you want to load a library into R, for you to be able to use the functionality and the data sets that come with those libraries, you have to type the command library and then open parentheses, the name of the library, and close parentheses. So for example, you can load the cluster and parallel packages. Also, package and library are just interchangeable words for the same thing. So you can type library cluster like this, and the program should run, and it will load the cluster library. If there's no output to the screen, then that's a good thing. It means it worked. And it means that you now have access to all of the functions and data sets that come with the cluster library. You can do the same thing for the parallel library, and you should have access, and that should do exactly the same thing. It should give you no output, and from there, you'll have access to all of the parallel computing functionality that comes with the parallel library. Also, if you want to install separate packages that don't come with a standard, generally the way to figure out if a library comes standard with R or not is to go look up the library, look up what the command to load it would be, and then try running library and then the name of the library in R itself. And if it gives you an error, so something like this, I don't have this library, then you'll want to do something. Then you'll want to install the library, and you can do that by typing install.packages and then the name of the library. So, for example, this install.packages command will install the psych library from the R standard repository of libraries. Just as a note, if you're working on Open On Demand, that command will not work because you have to be connected directly to the internet in order for the install.packages to work. And Open On Demand does not, even though it looks like it's directly connected to the internet, it isn't. There's some proxy magic going on in the background. So also, one way to figure out what data sets you have available in R, just the ones that are built in, you can type the data command with open parentheses and close parentheses right after it. That will print either to the command window or it'll print to the results window right above it a whole list of data sets that are currently available in your workspace. So if you've loaded other libraries, those will be lit. Then this data command will list everything, including the things that are the data sets that are available in the base library in your base environment, as well as the data sets that are available in the libraries that you've loaded. And there is a huge list of those. Also, if you type inside of that data command, package equals, like will show up on the next slide here, like package equals cluster, then you can actually filter down, and what the results will show is only the data sets that are available that are built into the cluster or to the library that you specified. So in this case, typing data package equals cluster in single quotation marks will show only the data sets that are available that are part of the cluster library. So for the purposes of this presentation, we'll be using 3 libraries that should be available by default on most systems. Again, if you're working on your home computer and one of these libraries doesn't work, you can type install.packages and the name of the library in single quotation marks, and it should install it for you. The 3 that we're going to use today are going to be the parallel, the cluster, and the datasets libraries. The parallel package implement is just a package that implements simple parallel computing functionality, which is really useful when you're trying to do like the same thing over and over and over again. Parallel computation allows you to sort of do all of those. It allows you to break it up into like 5 of them at a time in sequences of 5. We will also be using the MT-CARS dataset, which comes standard with R 4.1 and I think pretty much every other R version too. You may need to load the datasets package in order to get access to that though. So coming up next, we'll actually go into doing statistical analysis with R. So next up, we're going to do just some basic statistical analysis to show you how to get up and running doing some really simple things like linear regression, ANOVA, things like that in R. So if we load the datasets library and then create a variable called datasets and assign the MT-CARS dataset to that, which you can do just by following the commands on the screen. The arrow pointing to something is basically is called an assignment operator, and what it means is that I'm assigning whatever's the arrow is called an assignment operator, and what that means is take whatever's on the right hand side, take whatever's on the side of the arrow that the arrow is not pointing to, and give it the name that the arrow is pointing to. So in this case, we're essentially giving the MT-CARS dataset a nickname called dataset. So the next thing we can do is if we want to just get a summary statistic for just the standard, mean, median, quartile summary statistics for the miles per gallon column of the MT cars data set, we can type summary data set, summary open parentheses data set, and then MPG in brackets and single quotation marks like you see on the screen. And that will print out a simple list of minimum, first quartile, third quartile, median, mean, and maximum, your standard summary statistics for that column. And you can do this for any of the columns that are in the data set. And ignore the words that are on there. I thought I changed that, but apparently I didn't. Those are not SAT and ACT scores. Sorry. So one thing to keep in mind about R is that not all functions handle missing data very well. So if you're working with anytime you work with real world data sets, you're gonna have missing data. There's gonna be somewhere where the sensor didn't pick up the temperature right. There was a glitch in the computer or something, or a bird came by and picked up the sensor and ate it. So anytime where there's missing data, generally in R it's going to be represented by the letters NA and capital. And NA just means is one of a few different ways of representing missing data, but NA is the most common. Now, one of the things that's really important to know about missing data with R functions is that not all functions will do what you want or what you would expect with that. So if we were to create like a simple little list of data, which you can create a list in R by typing C open parentheses and then the list of numbers you want, and then close parentheses. That'll create what's called a column vector. So it'll give you just a list of numbers. If we put an NA in that list, and then we try and take the mean of that, the result is going to be NA, which that's not what we want. So there are ways of getting rid of missing data, and one of the ways is that you can take missing and then type na.omit and then missing in there. The problem with missing data, and particularly things with getting rid of missing data within individual data sets, and we'll see examples of this later on, is that whenever you eliminate that missing variable, you get rid of the whole column. So if you get rid of the whole row. So if you've got a whole bunch of different variables that you record for each sample. So if you're looking at temperature, dew point, water saturation or something for a whole bunch of different points within like a little valley somewhere. And for some reason, the temperature sensor doesn't work at one point, but all the other sensors work just fine. You may find that you have to get rid of all the other measurements for the observation that there was missing data for, which is not fun. But there are ways around it. You can either interpolate that value, which usually just means take whatever is on the left and the right side and then take the average, or you can assign it a value of 0, which is not always good, but sometimes you can get away with that. So just be aware that our functionality, so our functions, some of them will handle missing data and will deal with them in the background automatically. Many will not. And so if you're going through a whole set of statistical analyses and all of a sudden your results turn into NA, one of the functions that you ran did not handle the missing values correctly. And we'll see a number of examples of functions that do this. Another thing we can do with R is simple linear regression. Linear regression in R is done with the LM command, and that just means linear model. You can specify what variables you want to regress on. So for example, with the data set that we have here, if we want to specify a linear model that takes into account the weight of the car, the horsepower of the car, and the cylinder of the car, and also for anybody who's watching, weight should be WT, not weight. So keep that in mind. So if you type dataset $, weight, it should be dataset $, WT. So what we're doing here is we're basically saying, can we predict what the car's miles per gallon will be based on its weight, its horsepower, and the number of cylinders it has? And we're doing this by using a simple linear model, and we're regressing on the weight, horsepower, and cylinders. And when you type this and hit enter, you probably won't get any output, but that's okay because that means it worked. If you then type the name model, just model and then enter, then you'll see a whole bunch of output that will give you a summary of the model you just created. So it'll give you coefficients, it'll give you the intercept, and those coefficients are basically the betas for each of the variables. And by doing this, we can specify simple linear models for pretty much any set of variables we want. R also has a bunch of other functionality for linear models. You can also there's logistic regression you can do, there's generalized linear models, and there's a whole host of other ones. There's multiple linear regression. I think there's also Gaussian process regression. There's a handful of others. But linear models are one of the more important ones. And also be aware that you may run into problems again if there's missing data. So once we've got the model, we can then get some important statistics out of that model. We can use the confint command on the model and then pass model to it by type. And what that will do is it'll give you the confidence intervals for each of the variables. So you can look at the confidence intervals for each of the variables for each of the regressor variables. You can also use the ANOVA command to compute an analysis of variance on each of the regressors in the model. And that will also give you significance codes, which is basically just the alpha value that you may have seen in basic statistics. So if you have an alpha level of like 0.001, it'll come with 3 stars after it at the very end. An alpha value of 0.01 will have 2 stars after it, and a period will be at the 0.1 alpha value or confidence level. So these kinds of things are really important because by looking at the significance codes and by looking at ANOVAs and confidence intervals for each of the regressors you have in your model, you can look at these and pick out which variables you think are the most important, and that can really help you if you have a data set that is very, very, very high dimensional. You can also look at the residuals of the model by typing residuals and then model. And what that'll do is that'll just give you the distance. That'll just give you the root mean squared distance between. Well, no, that'll just give you the distance between each of the data points and the corresponding point on the line in the model that you created. So by looking at the residuals, you can actually tell things like just how good of a model is this, and how closely does it line up with the actual data points that I have. Another thing we can do is do something called GLM, which is R's concept of sort of generalized linear models and also generalized anything models. So you can type GLM, and then you can specify the variable you want to predict, and after the tilde sign, you can specify the formula for the variables you want to predict, and how you think they're related to one another. in this case, we're just doing data set. We're looking at cylinders times the difference between weight and horsepower. And this is just this is just one of many different formulas you could specify. Family Gaussian just means that everything's assumed to be a normal distribution, and data equals data set means that in this case it's just specifying that that the data set variable, which is MT cars in our example, is the full data set that we're looking at. Some functions will want access to the whole data set instead of just the variables that you give it. And then if you type that and hit enter, it will probably not give you any output, but that's good because it means it worked. And then if you type GLM model again and hit enter, you'll again get this whole bunch of output that'll give you things like residual deviance, a KK, and I'm not going to be able to pronounce that, a KK information criterion, AIC. You can also get things like degrees of freedom, the coefficients, the betas for your model, the intercepts, and a whole bunch of information from that. Much like the LM model, we can also do almost all the same things we could do with the LM model with the GLM model. You can type conf int and get the confidence intervals for each of the regressors. You can also type ANOVA and or type ANOVA with the model in it. You can get the analysis of variance for each of the regressors in the model. And you can also do residuals with that too if you'd like. So the next thing we can look at is simple ANOVAs, univariate ANOVAs. So and also covariance matrices. So if you want to get the covariance matrix for your data set, you can type cov, COV, and data set. Be aware again that this covariance function does not handle missing data very well. So if you have NAs in your data set, you will see NAs show up in your covariance matrix. And in the next slide here, there's actually a way to get around that. A lot of functions in R will have an option called use, and use equals in quotation marks complete.obs means only consider complete observations. So observations that don't have any NAs in them. Anything that has NAs, omit those. Most of the standard functions in R, like mean, variance, summary, will have this option. Covariance is one of them. So this is one way of getting around. Missing data in R. And if we do that with our data set, any NAs that would have been in that data set will be gone, and we'll get the covariance matrix based on all the observations that didn't have any missing data in it. But again, the use complete.observations option does come at a price. It comes at the price of you have to get rid of the entire column of data, or the entire row of data, that entire observation. So if you have an observation with 100 variables and only one of them has an NA in it, that complete.observation will throw out that entire row. So there are better ways of dealing with that, but this is sort of the default way. You can also in order to get the correlation matrix also, you can type COR in dataset, and that will give you the standard correlation matrix for the data set we're working with. Once again, the correlation data set also by default will not handle missing data. So you have to use the use complete.observations if you have missing data in your data set, or you have to make sure to get rid of all of the NAs by either interpolating them or assigning them to a default value. And again, this slide here is just a example of showing how to compute the correlation matrix with the complete.observations. Another thing we can do is simple univariate analysis of variance. So if you want to look at the analysis of variance, if you want to do an analysis of variance between one dependent variable and one response variable. For example, in this case, if we want to look at the analysis of variance between miles per gallon and cylinders, we can type AOV, dataset $MPG, and tilde dataset $CYL. I should also mention that the dollar sign between dataset and MPG means column. So whenever you see a variable dollar sign, another name, that means an entity, an element of that data set. So in this case, our data set comes in rows and columns. So the dollar sign means columns. So in this case, we're looking at the MPG column of our data set and the CYL column of our data set. And when you do that, and when you type this, it will again give you no direct output. But if you type ANOVA 1, then you'll get, if you type ANOVA 1 or whatever name you assigned the analysis of variance, you will get a whole list of output, which will give you back the way that you called analysis of variance, or the information that you gave to the analysis of variance function. It will also give you the terms that you asked for, including it'll also give you the standard terms like sum of squares, degrees of freedom, and it'll look at the dependent variable and the residuals. It'll also give you the standard error, and it will often tell you estimated effects may be unbalanced. So yeah, that just means that you have to be really careful which columns you choose. You have to be careful what data you choose. Also, much like the generalized linear models and the standard linear models, we can also get summary statistics of the analysis of variance itself by typing summary.AOV. And this will give us the degrees of freedom, the sum of squares, the mean squared error, the F value, and the probability value. It'll also give you significance codes. So this can help you determine whether or not the variable that you think your response variable depends on is actually significant. So in this case, we looked at cylinders versus miles per gallon. And this actually has a very, very high significance code. So it most likely means that we picked a good column to think that our miles per gallon column depends on. So in this case, it means that miles per gallon really does probably pretty heavily depend on the number of cylinders, which kind of makes sense. You can also look at multivariate analysis of variance as well. There is a command in R called MANOVA, M-A-N-O-V-A. And what you can do here is you can specify more than one response variable by using something called cbind. And cbind basically says, take any number of columns of your data set and bind them together into one thing, basically one table. This is going to be the matrix of response variables that we want to look at. And then the tilde means that you're specifying another set of variables that you think what's on the left-hand side depends on. In this case, we're choosing the weight column and the cylinder column. And again, once you hit enter, again, it should not spit out any output, but once you type MOV1 or the name that you gave them, the multivariate analysis of variance, you'll get a whole bunch of data output that is pretty much the same as you had with univariate analysis of variance. The only difference is that now there'll be multiple response variables. So you'll get the only difference that now there will be multiple response variables and also there could be multiple dependent variables. So you'll get to see how those variables interact with one another. Once again, you can take summary statistics of the multivariate analysis of variance. You can type summary.MANOVA and the name that you gave the multivariate analysis of variance, and this will give you pretty much exactly the same thing that you had for the univariate analysis of variance. It'll give you each of the dependent variables, the degrees of freedom, and a whole bunch of other information. And like pretty much everything else, it will give you a significance code, so you can decide whether or not the columns that you chose really are statistically significant. You can decide whether or not your response for the relationship between your response variables and your dependent variables actually matters. R also has functions for various other things. If you wanted to do analysis of covariance or multivariate analysis of covariance, there's the ANCOVA, or that is also possible. There is no ANCOVA in the base R library, but if you look through the giant list of available R packages, then there's guaranteed to be at least 5 or 6 that have an ANCOVA function, and they'll very likely work in very similar ways, and they'll likely compute the ANCOVA in very similar ways. But that's one of the main advantages of R, is that even if the base package doesn't come with the function you need, or doesn't come with the analysis you need, there's bound to be a free open source library out there that does have it. So all you have to do is go look through the repository of libraries, and you will pretty much you'll almost certainly find it. But continuing with the basics of R, you can also do multivariate, some basic multivariate statistics with R. You can do factor analysis with R, and if you've ever taken multivariate statistics, factor analysis is sort of like the old school primary way of doing dimensionality reduction. So what you can do, you can use the factor analysis function, which is on the screen here, and you can type the name of the data set and the number of factors that you want to keep. So in this case, we're looking at the MT-CARS data set, which has looks like 9 or 10 oh, actually it has 11 variables. So it's got 11 columns, and we want to create a lower dimensional representation of that data set that has only 4 variables. So factor analysis is one way of doing that, and it's sort of the classical way of doing that. Many of the other dimensionality reduction methods, like if you've ever heard of principal components analysis, which we'll see how to do in a minute here, or multidimensional scaling, almost all of those came after factor analysis. And some of them can even be recast as a type of factor analysis. But the basic R library has a lot of these functionalities already built in, so you don't really have to think too much about exactly how to implement it, or exactly how it works. You can just type the command and let it do its work. So there are actually two basic principal components analysis functions in R. There's PRComp and there's PrinComp, and they differ they only really differ in the details of their implementation. One of them is, and not in any way that really matters. One of them computes the principal components by using something called the singular value decomposition, and one of them computes the principal components based on the eigenvectors of the data set. For the most part, these details don't really matter that much. For some very specific analyses, it might matter. If you're working with very, very large data sets, the singular value decomposition which is PRComp, is usually the faster one. But if you're working with regular sized data sets, even up to a few hundred thousand rows, you're probably fine using either one. But the first thing we need to do is we need to clean the data. So if you have missing data in your data set, one way to get rid of it is you can use na.omit, and we can create a new variable called clean data, and we can say clean data equals na.omit data set, like you'll see on the first line of code there on the screen. And that will basically do what the same thing that use equals complete.observations would do. It'll take your data set, it'll pull out everything that has missing data, and it will give you back a data set with only observations, or with only rows and observations that don't have any missing data. And this is important because principal components analysis can start to act a little weird if you do have missing data. So once we have the clean data, we can type prcomp and clean data, and that will give us the principal components analysis. It'll give us the standard deviations for each of the components, and it will also give us the components themselves. Now, principal components analysis is kind of interesting in the sense that each of the standard deviations there can be used to determine which of the components contribute the most to the variance. And if you were to plot the standard deviations just on a standard histogram, you'd get a plot that kind of looks like that. Sort of the first component has a really high standard deviation, and then each component following that has slightly less, and then eventually going down to none. And this is actually really useful because you can look at the standard deviations in the principal components, and you can look for the ones that have the largest number of, or the highest amount of standard deviation. And from that, you can determine how many principal components you want to retain. So if you think 3 or 4 principal components contains enough variance to explain what's going on in your data set, then you can just keep 3, and then you can use that lower dimensional data set to continue working. You can also use the prncomp function, and the prncomp function will give you things that it'll give you a little bit different output, but the results are pretty much the same. The standard deviations will be almost identical. So are there any questions on factor analysis or principal components analysis, or how you do those in R? Anybody online? All right. So you can also do k-means clustering, and clustering analysis is really useful for finding groups in your data. So there's a k-means function in the base library of R, and you have to make sure that you give it the clean data set that we created on the last slide. And you also have to give the k-means function the number of groups you expect to see in your data set. K-means is kind of interesting in the sense that it presumes that you know how many groups that you expect to see. There are actually more recent methods that have been developed that are trying to get around the need for you to know how many groups you have ahead of time, but those are most likely going to be in non-standard packages. So once you type k-means and with the clean data, the number of groups you expect, you will either get no output, in which case you have to type the name of the variable you assigned it to, or you'll get a whole bunch of output that looks kind of like this. Each one of these indicates the center of the cluster. This can actually be really useful because if you look at the coordinates of the cluster means, which is the first group of data you have there, then you can look to see if any of them are kind of really close to each other or even right on top of each other. And you can also, in the next slide, we can also plot these clusters and see if any of them are right on top of each other. If any of them are on top of each other, then we know that we asked for too many clusters. So in this case, there's clearly at least a couple of clusters, but the two clusters at the bottom there are really close to each other. So maybe there were only 3 groups. In order to get this graph here, you can type library cluster, and you can either just type clustplot, clean data, $cluster, color equals true. The line above and below the clustplot are just there to allow you to basically take a picture of the plot and save it to an image file on your computer. So if you're working through Open On Demand, you may want to do that. But if you're working on your own computer, you can ignore the JPEG and the dev.auth lines. And you should get something that looks pretty much exactly like this figure here on the right. So are there any questions so far? Any questions?
Yeah.
Yep.
I'm answering it right now, but is there anything similar to the help in MATLAB where you could enter like help k-means and get an explanation of what kinds of input to expect, etc.?
That's a very good question, actually. So the question, just to make sure everybody heard it, the question was, is there anything similar to the help function in MATLAB, which if you type help in the name of a function, it will give you a little bit of documentation telling you what it expects you to what information the function expects you to give it and what you can expect to get back from it. And there is an R. There's the question mark function. So you can type question mark in front of a function, so like question mark dist or question mark hclust, and that will actually give you it'll give you that information. So I can show you that. Like for example, if I type here and I type question mark hclust, it will print over here. It'll print over on the right-hand side of the screen the documentation and information for the hclust function, and you can use that question mark for pretty much any function in R and any function for any of the libraries you've loaded. So speaking of the hclust function, actually, hclust is a way of doing hierarchical clustering. So if you work with bioinformatics or specifically phylogenetics, and you've seen any of those like dendrograms or phylogenetic trees that they create, one of the sort of classical methods of doing that is using hierarchical clustering. And the function hclust in R will allow you to take your data set and compute a clustering from that. The first thing you have to do is compute a distance matrix, and you can do that by typing dist and clean data, and that will compute the distance matrix, which is basically just looking at how similar or how different each of your variables are to one another. And then once you have that distance matrix, you can type hclust, and in this case, you can either type method equals ward.d, or you can leave method out entirely, and that will give you a hierarchical clustering, which we can then plot as a dendrogram. Ward.d is Ward's method, and it's one of a number of different clustering methods, and it's one of the more popular ones in bioinformatics. Basically, what it does is it sort of minimizes internal or within group variance, and that has a way of producing a lot nicer dendrograms. But if you leave that out, it will default to complete linkage clustering, which is sort of the standard default clustering. And this time we can actually plot it without using the clustplot function. And once my slides decide to change there, you can actually just type plot clusters, which clusters being the name of the variable we gave to the hclust result. And when you type that, you'll get a dendrogram that looks kind of like what you see on the right here. And this is also useful for looking at, how many groups do you have in your data, and how are those groups related to one another. So There are also a whole bunch of other multivariate techniques that R has the ability to do. You can do correspondence analysis, canonical correlation analysis. There's an MDS function for multidimensional scaling. There's canonical correspondence analysis. There's several different flavors of discriminant analysis. There's linear, quadratic, a handful of others. And there are a bunch of other techniques that you can do in R. What I showed here is just a small sampling of what R is capable of. So parallel computations in R. As I was said in the beginning of the presentation, a lot of times, especially if you're working with huge data sets, you're going to run into a situation where your one single CPU processor is just not enough, or the amount of, and as a result, it's going to take forever. It's really slow, and you can feel the bottom of your laptop burning up. So this is where parallel computation comes into play. A lot of times, particularly with statistical analysis, you're doing the same thing over and over and over and over and over again, many, many times. And so you can actually break that up and do a lot of those things that you were doing over and over and over again. Instead of doing them one at a time, you can break it up and do a bunch of them at once. So parallel computing allows you to do that, and R has some very nice and easy ways of allowing you to do that. There are some complications though. I mean, you need to be, for example, if you need to pass information between various processes that are running in parallel, that can add some complication. And if a central data set is being updated by multiple processes at the same time, you need to make sure that only one is updating it that only one process is updating the data, the central data table or the central results at any given time. So there's two different options with parallel computing. There's shared memory, which basically makes it so that you have to really think about what's being updated at any given time. And then there's message passing, where you basically take a copy of what a different process needs to know, and then you send it to that process. And that can be a little slower, but it's a lot more versatile. R has a whole slew of different parallel computation libraries. The parallel library that I talked about earlier on is sort of the default one. It is the way of the parallel library comes standard with most R installations, and it gives you a whole bunch of functionality to kind of abstract away having to worry about, what's being updated when and what's being passed back and forth. So again, if we load the parallel library, we'll again get access to all of the basic parallel functionality. And the first thing you need to do with the parallel library is you need to do something called making a cluster. And this basically means you need to tell R needs to know how many CPUs it's got access to. And you can do that by typing n cores equals detect cores. And another thing I should mention is that equals and arrow pointing backwards are the same thing in R. So you can do n cores equals detect cores, open parentheses, close parentheses, -1. And that -1 just means, and that -1 just has to do with how R starts counting. Most computers, when they list information, they start from 0. So if you've got like a shopping list, you've got like items 1, 2, 3, 4, 5. Most computers will start counting from 0. So they'll have 0, 1, 2, 3, 4. In this case, the -1 here is just translating from R, which starts counting it from 1, to the computer, which starts counting from 0. And then once you do that, you'll get the total number of cores the computer has access to. And then you can type the make cluster command, and that will make a group in R of CPUs that the program has access to. And then once you've done that, you can use the par lapply function. And the par lapply function is one of several functions that will allow you, that can actually allow you to run the same command over multiple different columns in your data, all in parallel. So in this case, we want to compute the average of each column in our data set, and we want to do it in parallel instead of doing it all at once. So we can type the par lapply function, and the first thing we have to give it is the name of the cluster, so CL in our case, then the name of the data set, which is just clean data in our case. Again, you have to be careful to make sure to give it data that doesn't have missing values. And then we're telling it what function we want it to compute on each of the columns in our data. In this case, the mean. And when you hit enter, it probably won't give you any output, but when you type means, it will give you all of the average, each average for each of the columns in your data set. And this will be a lot. And this, you may not see any difference immediately with this, but if you were working on a data set that had 10,000 columns, the par lapply function will be a lot faster than trying to just compute each of the averages one at a time. Once again, the Research Computing Center has access to R. If you ever need the ability to do really large computations on R, or on data sets in R, or you ever need the ability to parallelize your computations across a whole bunch of different cores, basically to do that par lapply, but you need 48 CPUs, then we are the people to talk to. We also have a number of other statistical resources available. So R is not so even in the outside world, outside of just RCC, R is not your only option. If you're familiar with Python, Python has a number of statistical packages that are available, and RCC teaches workshops on Python as well. So if you're interested in learning that, keep an eye out for that, and we can teach that. We also have a number of libraries for Python available. There's also a whole slew of other statistical libraries that both RCC has available, and most of which, except MATLAB and CUDNN, most everything else there is free. So, and Stata. So most everything there is free. So if you don't want to use RCC, you can also look at those. You can also look at downloading those to your own computer, and you can use those. On this last slide here, here's a few links to a bunch of important references for R. So the so stat.ethz.ch/R manual is the basic. That's the basic user's manual for R, and that's one of the first things you'll want to look at. rdocumentation.org has documentation for almost every function in almost every library I've ever seen. So that's a good place to look for. That's a good place to look if you're looking for documentation if you're looking for specific packages or functionality. Thank you all for attending. If you all have any questions, please let me know. And I'm going to stick around for a few minutes afterwards.